Hello, and thank you for your interest in our work. My name is Alexander Grimm. I performed this experiment when I was a postdoctoral associate in the lab of Michel Devoret at Yale University, but I have since moved on to a new position at PSI Switzerland. Let me start by acknowledging my coworkers, in particular Nick Frattini, who is the grad student who worked with me on this project, and Shruti Puri, who provided us with theory support. If you're interested in learning more about our work, you can find it on the archive here. So I will be speaking about an experiment in superconducting circuits, which is part of our effort towards quantum error correction. And what we are doing in particular is we are working with so-called Schrödinger cat states, which are superpositions of coherent states in a superconducting resonator. I'll get back to that in a couple of slides, but let me first situate our efforts in the larger context of quantum error correction. Quantum information can be encoded into superpositions of the two energy levels of a quantum two-level system. That is what is called a physical qubit. Such a physical qubit always suffers from two types of errors, which can be broken down into bit flips, which are flips of the bit value, and phase flips, which are flips of the sign of the superposition. Now, if you want to build a larger quantum machine from these physical qubits, you will eventually run into a limitation just because these errors compound. Now, quantum error correction tackles this problem by redundantly encoding quantum information, using, for instance, a system that is made from many coupled physical qubits. That's what is done in the CSS codes, such as the repetition codes, or by extension, the surface codes. Another approach is to use a portion of the energy levels in the infinite ladder of energy levels in a harmonic oscillator. That's what's done in the bosonic codes, which are sometimes termed hardware efficient just because they involve fewer physical components. Now, both of these approaches, I should point out, rely on auxiliary systems in order to detect and correct errors. And in general, these auxiliary systems are themselves physical qubits suffering from bit flips and phase flips. And while they couple to these logical qubits that I'm showing in these blue boxes here, their errors can again feed forward into the logical qubit. The system I will speak about is somewhere in between these two approaches. It is based on a simple physical implementation, such as the physical qubits in the CSS codes, but it is a bosonic code. And this system called the Cat-qubit has the possibility of suppressing one error via the encoding. Let's say it suppresses phase flips, and let's think about the extreme case where it fully suppresses them. Well, then quantum error correction is reduced to the case of classical error correction that only deals with bit flips, which is of course much simpler. But even if it doesn't fully get rid of phase flips, but just strongly suppresses them with respect to the bit flips, there is still a lot to be gained. And that has been shown in these papers for the general case of qubits that have a strong imbalance between bit flips and phase flips, showing that it can increase the error threshold in repetition codes or surface codes if it is used as a logical qubit component. There also has been recent theory work specifically focusing on the Cat-qubits that I'll be talking about, showing the same thing. Another use for these qubits is to use them as auxiliary systems for error detection in other quantum error correction codes, such as different bosonic codes, but also in the surface code. And it has been shown that this can lead to fault-tolerant error syndrome measurements, meaning that you don't have errors feeding forward into the logical qubits anymore. So these two things together show that these Cat qubits can significantly decrease the hardware complexity of quantum error correction. There's, however, a flip side to the medal, and that is that these Cat qubits, as I said earlier, are based on superpositions of coherent states, and coherent states are, of course, highly excited states of an oscillator. So if you don't do anything to stabilize them, they will decay to vacuum over time. And that is what I will address in the following slides. Now I'll start with a simple case where we stabilize just a single coherent state. And we'll do this in the absence of dissipation. Now if you applied a resonant drive to an oscillator in the absence of dissipation, you will just get growing energy and not a coherent state. If instead you apply this drive off resonantly, as demonstrated or as shown by this Hamiltonian here, then you get a stable coherent state, and that stable coherent state will depend on the strength of this coherent drive that you're applying and on the detuning of the drive from the resonator resonance frequency delta. And this is what I'm showing you here, where you have alpha, the coherent state amplitude, which depends on the ratio between the drive strength epsilon and the detuning delta. We can plot the classical energy landscape corresponding to this Hamiltonian in phase space, where you have here the real and imaginary phase space coordinates, which might as well also be the quadratures if you prefer that. And you see that this Hamiltonian has a single extremum corresponding to the position of this coherent state alpha. And this phase space representation just shows you the amplitude of the oscillation, which is given by the distance from the origin, and its phase, which is given by the angle with the real axis. So here it's 0, it's along the real axis. Now, one coherent state is of course not enough to encode a qubit. You need at least two coherent states that are stable simultaneously. In this case, this wouldn't be possible, because while coherent states are eigenstates of the annihilation operator of the field in the resonator A, two out-of-phase coherent states, for instance, bring out different eigenvalues, so this operator distinguishes between the two. You can play a simple trick, however, and you can just square this operator. Now you have E squared, and this doesn't distinguish anymore between two out-of-phase coherent states, plus and minus alpha. And now we go and we apply the same trick to the Hamiltonian. And what you get is this Hamiltonian here, where you have a single mode squeezing, so a 2-photon drive of strength epsilon 2, and you have a photon number dependent detuning, which is of course nothing else than the Kerr effect of strength K, the Kerr constant. Let's do the same thing as before and plot the classical energy landscape corresponding to this Hamiltonian. And what you see now is that we have two extrema corresponding to the positions of two coherent states, plus and minus alpha, with an amplitude and phase that is determined now by the square root of the ratio between the single mode squeezing drive, strength epsilon 2, and the Kerr constant. Or a more precise way of seeing how this works is by taking this Hamiltonian here and factorizing it in this way. This is the same Hamiltonian. And what you see now is this second parenthesis here annihilates these two coherent states, plus and minus alpha, meaning that they are degenerate eigenstates of the quantum Hamiltonian and do not evolve in time. What's more is there's an energy gap to all the other eigenstates, which is proportional to 4 times the Kerr constant times alpha squared, so the photon number in the coherent states, or just 4 times the single mode squeezing strength. And this additionally contributes to the stabilization of these coherent states, which prevents them from decaying to vacuum over time. Now, let me mention that there's a different way of stabilizing these coherent states, which is based on the interplay between a 2-photon drive and dissipation, and there have been some really exciting recent results on this. But what we'll focus on here in the rest of this talk is this purely Hamiltonian approach, which has been originally predicted about 20 years ago and has been implemented in this experimental work for the first time in order to stabilize an error-protected qubit. Now, how do we actually encode the qubit into these coherent states? Here I'm showing you the encoding of this Cat-qubit. And you can see that we are placing the coherent states plus and minus alpha along the x-axis, and then the other axes are spanned by their superpositions. For instance, along Z, we have the even and odd superpositions of these two coherent states, which are called even and odd Schrödinger Cat states, and they involve only, respectively, even or odd photon numbers. In addition to the cats that I'm showing you for all 6 cardinal points, I'm also showing you these Wigner function phase space representations. And let me quickly explain those to you. What you see here is the Wigner function of an even cat state, and there's the 2 constituent coherent states represented by these disks. And then there is fringes in the middle which show that they are in a quantum superposition. And the center point of this Wigner function gives you some valuable information, namely the photon number parity. Here it's red, which means +1, meaning even photon number parity. Down here, for instance, it's blue, meaning -1, so odd photon number parity. So what are the error protection capabilities of this qubit? Well, in this qubit, phase flips are suppressed exponentially in the photon number, where the photon number is given by the amplitude of the coherent state squared. And you can understand this intuitively by seeing that noise processes in an oscillator on short time scales displace you only locally in phase space. And the fact that these two coherent states are very far apart in phase space means that it's difficult for noise processes to flip you between them. Bit flips, on the other hand, are increased linearly in the photon number, and that's because if you stochastically lose a photon in this encoding, then this flips the photon number parity. So for instance, you flip from an even cat to an odd cat and vice versa, and that flips along this axis. In a way, what this means is that if you have more photons in your cat, it's more likely to lose a photon. And in fact, you can write down an approximation for this bit flip rate, which is given by 2 times the single photon loss rate times the photon number in the cat. Now, you see there's an exponential suppression of the phase flip rate and a linear increase of the bit flip rate. And that means that this can be a very good qubit as long as you can perform all operations much faster than the now decreased bit flip rate. So speaking of operations, what can we do here? Well, we can perform a continuous X-gate, which is based on applying an additional single photon drive that lifts the degeneracy between plus and minus alpha, and I'll explain that in detail later. And then we can do a discrete Z pi over 2 rotation based on switching the squeezing drive off and letting Kerr act, and I'll briefly touch on this later. What I want to say here is just that these two together are enough to reach any point on the surface of the Bloch sphere. And what's crucial here is that the important operations on these qubits scale inversely with Kerr. And that means that Kerr doesn't only help us stabilize this qubit, it also helps us to perform fast operations. And that is quite different from a lot of other bosonic codes in superconducting circuits where Kerr is a problem because it deforms the code states, especially if they involve a lot of photons. No, here's the opposite. Here, Kerr is our friend and not our enemy. So how are we actually implementing this system? Here's a picture of our implementation. And what you see here is the lower half of a copper microwave cavity that acts as our readout resonator. And in that cavity, you have this sapphire chip on which there is an aluminum oxide structure, and that's the mode that will host the Kerr-Cat qubit. Here's a schematic of this structure with 2 big capacitive pads shunted by a nonlinear inductance. And I'm showing you here an SEM image of this nonlinear inductance called a SNAIL element, which consists of a small chosen junction together with 3 large chosen junctions in a superconducting ring, which additionally can be threaded by a magnetic flux bias. We use this to engineer the nonlinearity of our system in order to implement the Hamiltonian that I showed you earlier, where the 4th order nonlinearity of our system directly implements the Kerr, and then the 3rd order nonlinearity combined with a microwave pump that we apply is going to give us the squeezing drive. We simply apply this pump at 2 times the mode frequency, and a photon at 2 times omega A through 3-wave mixing gets converted into 2 photons at the mode frequency omega A. We also get stark shifts when we apply this pump, which we calibrate out in our experiment. Here are some system parameters. The frequency of our mode is 6 GHz. Its single photon lifetime is 15.5 microseconds. Its T2 Ramsey coherence time is 3.4 microseconds. And what we engineered here for the Kerr nonlinearity is 6.7 megahertz. And in this system, we can achieve a single mode squeezing strength of 17.5 megahertz. meaning that since the photon number is dependent on the ratio between these two quantities, we can reach about 2.6 photons here. So let me just stress again that the mode that the Kerr-Cat will live in is going to be the mode on this sapphire chip here. And this mode actually implements 2 qubits for the price of 1. So what do I mean by that? Well, if we do not apply the single mode squeezing drive, then we are just left with this Hamiltonian here, which just has the Kerr. And that, to good approximation, is actually the Hamiltonian of a standard superconducting Transmon qubit, where you can selectively address the transition between the vacuum state and the one photon Fock state, and you encode a qubit into superpositions of these two states. And this is a system we know very well, that we control very well. So we have all continuous single qubit gates here, and we have the standard dispersive readout along the z-axis. On the other hand, if the single mode squeezing drive is on, then we are stabilizing the protected Kerr-Cat qubit that I described to you. And what's nice here is that we can actually adiabatically map between these two systems by ramping on and off the single mode squeezing drive slowly with respect to 1/Kerr. And this works because both of these Hamiltonians respect photon number parity, meaning that the even photon number parity vacuum state gets mapped onto the even cat, and the odd photon number parity one photon Fock state gets mapped onto the odd cat. And then of course you get a full mapping between the two Bloch spheres. And we'll use this in our experiment in order to initialize the Kerr-Cat qubit, but also to map it back onto the Fock state qubit and use the dispersive readout to read it out. Doing so, we will demonstrate different properties and effects in the Kerr-Cat qubit. For instance, I will first show you a Rabi around the x-axis, which will also serve as kind of a smoking gun experiment, showing that we can in fact stabilize this Kerr-Cat qubit. I will later show you a direct quantum non-demolition readout on the Kerr-Cat qubit, which doesn't use that mapping. I will also discuss the coherence times, and I will briefly discuss the continuous X and discrete C gate that we can do here. Now, let me start out by talking about this continuous Rabi around the x-axis. So as I mentioned earlier, the continuous X rotation is based on applying an additional coherent drive to the system of strength epsilon x here. What this does is it lifts the degeneracy between the two coherent states, plus and minus alpha, and it lifts the degeneracy by a quantity that you can work out to be the real part of 4 times alpha times the strength of this additional drive. And that also gives you the Rabi rate, because now the two coherent states are picking up a dynamic phase with respect to each other, meaning that there is an oscillation around the x-axis of the encoded qubit between their superposition states. Now, what's special here is that the relative phase between this additional drive that we're applying and the coherent state amplitude matters. And we'll use that to distinguish this from the case of just a regular 2-level system and Rabi oscillations on that. The experiment that we'll do here is based on 3 different drives. One is the squeezing drive that I mentioned, the other one is the Rabi drive, which corresponds to this additional drive, and then the third one is the readout drive, used for dispersive readout on the Transmon qubit. Now, the experiment starts in vacuum on the Fock state qubit, and we slowly ramp up the single mode squeezing drive, which brings us to an even cat state. And then we leave it on for a varying amount of time, delta t, and during that time we also switch on the Rabi drive. We then switch the Rabi drive back off and map the resulting cat state back onto the Fock state qubit. And then we read out along the z-axis of the Fock state qubit. While we're doing this, we're also going to vary the Rabi drive phase and not only the time difference delta t. So first, I'll do a control experiment where we don't switch on the squeezing drive. Now we're just going to Rabi regular Fock state qubit. And here's the result of this experiment. On the color scale, you're seeing the 0 photon population fraction at the end of the experiment. Along this axis is the phase of the Rabi drive, and here is the time difference. And what you see is just a sinusoidal oscillation as a function of time that does not depend on the phase of the applied Rabi drive. And that's exactly what we would expect. Now, what happens if we switch on the squeezing drive with a small amplitude? Well, what you see is that the Rabi rate is starting to be suppressed at two specific phases, and these phases correspond to the values where the drive phase is 90 degrees out of phase with the phase of the coherent states. And if you now go and we crank the squeezing drive up even more to the value that we're pretty much using the rest of the experiment, well, then the Rabi rate is completely suppressed for these two values, validating the prediction of this expression. Now, later I will show you how we can use this process to perform gates on the Kerr-Cat qubit, and then we will, of course, operate at this phase difference where both alpha and epsilon x are aligned. And you can actually see that the Rabi oscillations here are faster than in the case of just the Fock state qubit, because now the Rabi rate also scales with the coherent state amplitude alpha. In this experiment, we have used the mapping back onto the Fock state qubit and the dispersive readout. But of course, if we want to use the Kerr-Cat qubit as an honest-to-goodness qubit, then we need to also be able to read it out directly. And that's what I will show you next. I will show you a quantum non-demolition readout along the x-axis of the Kerr-Cat qubit. We achieve this by applying an additional drive to our system at the difference frequency between the readout cavity frequency and the Kerr-Cat frequency. This, through the three-wave mixing present in our system, implements the following Hamiltonian, which is a frequency conversion Hamiltonian, that annihilates one excitation in the Kerr-Cat mode and creates an excitation in the readout cavity mode and vice versa. And if we project that Hamiltonian onto the Cat qubit basis, it's nothing else than a displacement of the readout cavity conditioned on the x state of the Kerr-Cat qubit, where this is the sigma x operator of the Kerr-Cat. To be completely precise, I'll show you what this does in the readout cavity phase space. Now, if we initialize our Kerr-Cat qubit along the plus x-axis, so along plus alpha, and we keep the stabilization on, and we now switch on this additional drive, then we will displace the readout cavity in one direction in its phase space. If, on the other hand, we initialize the Kerr-Cat in minus alpha, so along the other direction of its x-axis, the readout cavity will be displaced in the other direction in its phase space. And now the state of the readout cavity leaks into our measurement chain where it gets amplified, eventually demodulated and digitized. And then for each experiment that we run, we can attribute to it one position in the phase space. And we do this experiment 300,000 times to get a histogram in phase space, which I'm showing you here for the two cases where we have initialized in plus alpha and where we've initialized in minus alpha. And you see that the two histogram disks are well separated in our measurement. We can draw this dashed white line between them, meaning that we can implement a single shot readout. And that means if we just do a single measurement and it follows to the right of this line, we can say, oh, it was in plus alpha. If it's on the left of this line, we can say it was in minus alpha. This also allows us to quantify the fidelity of our measurement. And we define the uncorrected readout fidelity as 1 minus the probability of having tried to initialize in minus alpha but measure in plus alpha minus the complementary probability. It comes out to be 0.74, so 74%. But this is uncorrected, meaning specifically, for instance, it does not correct for state initialization errors, such as the thermal population of our Fock state qubit, which by itself contributes about 8% of infidelity. We can also quantify the quantum non-demolition aspect, meaning that if we measure the state of our Kerr-Cat qubit twice, we should get the same result. And it's defined in exactly this way. We average over the probability of, in two successive measurements, getting the same result plus alpha or the same result minus alpha both times. And here we find 0.85, so about 85%. So to summarize this slide, what we did here is we implemented a single shot witch coherent state readout along the x-axis of the Kerr-Cat qubit. And we will now use this to investigate the coherence properties of the Kerr-Cat qubit. First, we'll look at the X-state coherence. So what we do for this is we initialize the Fock state qubit along plus or minus x, and then we map that onto the Kerr-Cat qubit. We then wait for a variable amount of time, and then we perform this readout that I just explained to you. Here is what we get as a result of this experiment, where I'm showing you on this axis the x expectation value of the Kerr-Cat qubit as a function of time for initialization in plus alpha or minus alpha. Blue open circles are data points, and black solid lines are single exponential fits with a decay constant of 105 microseconds. And that's, of course, great news, because that means that our Kerr-Cat qubit is much longer lived than either of the two coherence times of the Fock qubit, which were 15.5 microseconds and 3.4 microseconds. We also expected there to be a reduction of the bit flip time. And this is indeed what we observe. So here I'm showing you the Y state and the Z state coherence, where we perform similar experiments. We just initialize along the Y and the Z axis in the corresponding states. And again, blue open circles are data points, and the black solid lines are single exponential fits. All of them have decay times of about 2.6 microseconds. That's close to what we expected. We expected the T1 of the so the single photon lifetime of the Fock state qubit to be divided by 2 times the photon number in the Kerr-Cat qubit, and that would have given 2.9 microseconds. But in reality, photon gain events, so A-dagger jump events, can also contribute to this bit flip time. And if we take that into account, then we get a value that pretty much reproduces the 2.6 microseconds. Now, the take-home message for this slide is that we're seeing this 30-fold increase of transverse relaxation time along the x-axis from 3.4 microseconds to 105 microseconds. But we're also seeing this decrease. And now what will basically be a figure of merit for our qubit is if we can apply gate operations to it much faster than this now reduced bit flip times. And that's what I want to characterize on the following slide. Here I will show you quantum process tomography of the gates that allow us to reach any point on the Bloch sphere on our Kerr-Cat qubit. But I'll start out by introducing this tomography just on the mapping process. So what we do for this tomography is we initialize first the Fock state qubit in any of the 6 cardinal points of its Bloch sphere. We then map that onto the Kerr-Cat qubit at a photon number of 2.6, which is also what we used in the other experiments. We pretty much immediately map that back, and then we do another sequence of pulses combined with dispersive readout on the Fock state qubit to measure the X, Y, and Z expectation values. That is a total of 18 experiments, and I'm showing you the result of these experiments in this Bloch sphere representation, where the markers tell you which state we tried to initialize the qubit in. So for instance, the orange square or the green diamond correspond to the plus or minus alpha states along the x-axis and so on. And the position of the marker tells you about the expectation value vector that we've measured. And what you're seeing is that they're all pointing along the right directions, along the right axis, but they all have shrunk to the inside of the Bloch sphere. And that's, of course, due to the loss of fidelity that, for instance, is due to decoherence during our ramp on and ramp off mapping pulses. Now we can characterize the fidelity of this process with the Pauli transfer matrix approach, and we find about 85%. Now, in a similar way, we can now characterize the fidelity of the gates that we do on this qubit. The first gate is going to be an x pi over 2 rotation, and that's based on this continuous x rotation that I showed you earlier. And it's basically just we're applying now a calibrated Gaussian pulse to our Kerr-Cat qubit, which takes about 24 nanoseconds, and it's calibrated so it does a pi over 2 rotation. And here's the result of the tomography. You see that it works. The x states are still along the x-axis, and all other states have rotated by 90 degrees around the x-axis. Again, we extract the fidelity, and this fidelity is again about 85%. And I'll get back to that in a second. Since we can do any angle around the x-axis, all we need is a discrete pi/2 rotation around the z-axis to reach any point on the Bloch sphere. And we can implement this by abruptly switching off the squeezing drive for a well-controlled amount of time, and then abruptly switching it back on. And it's basically based on the action of Kerr on the states of the Kerr-Cat qubit. We implement this experiment and we find a fidelity of about 81%, and the fidelity reduction here with respect to the other fidelities is just due to the fact that we have some experimental limitation in how quickly and for what exact time we can switch off this squeezing drive, which is basically limited by the sampling rate of our experimental system. Now, what you've noticed probably between these two fidelities of the mapping and the x/2 gate is that they're the same, and that means that we cannot resolve the infidelity that comes from our x/2 gate. We're mostly limited by state preparation and measurement. But we can estimate this infidelity by taking the ratio between the time that it takes to do the gate and the bit flip time. And that's about 0.01, so about 1%. And in fact, we are doing an additional experiment to confirm this, which indicates that this is in fact the infidelity that's contributed by decoherence and over rotations or leakage out of the encoding manifold in our gate. Now, what I've shown you here is that we can perform all single qubit gates in less than 40 nanoseconds, and that's of course significantly faster than the shortest decoherence time in our system. Now, where do we go from here? Well, there's a wealth of interesting experiments that we can do with this system. I've already mentioned the fault-tolerant error syndrome measurements on other quantum error correction codes, and I've already mentioned that we can build fully error-corrected qubits with very high error threshold, meaning also with high hardware efficiency out of these Cat-qubits. But there's more. I mean, they can be used for quantum simulation and adiabatic quantum computation, and they are in themselves interesting nonlinear and out of equilibrium physics. In fact, with this experiment, we've already extended our understanding of bifurcation in bistable quantum oscillators. So stay posted for more results that are to come soon, and I thank you for your attention. And since this is an online talk, if you have any questions, do not hesitate to contact me via email. Thank you.